The next speaker is Massimo Bettio from Carraro. He will talk again about temperature prediction. In this case, about temperature in a transfer box and comparison between numerical estimations and experimental data. Massimo is a hydraulic system specialist at Carraro. He has a master's degree in mechanical engineering from the University of Padova. He started his experience in virtual validation at Carraro in 2018 during his master thesis on the analysis of threaded connection for off-highway axles. He joined the hydraulic system team, where he currently supports testing and design activities of both axles and transmissions for off-highway applications. Massimo.
Thank you, Massimo, for the presentation. I'm Massimo Bettio, hydraulic system specialist of Carraro Group, and today we're going to talk about a comparison between experimental measurements and numerical estimations of temperatures on a transfer box for electric compact wheel loader applications. First of all, introduction of the company. Carraro Group is a leader in production of specialized tractors, gears, as well as power transmission systems for agricultural and construction equipment applications, as well as automotive industries and material handling. The headquarters of the group is in Campo d'Arsego, near Padua, and the group counts over 3,500 people, employees, all over our manufacturing plants in Argentina, Italy, India, and China. After a brief introduction and an explanation of the case study, we will see the particle model set up and simulation for estimate the heat transfer coefficient of the transfer box under investigations, and we will see the power losses formulation in according with the technical report of ISO 14179 part 2. And we will see how these two contributes have been used for the thermical steady state Particleworks and ANSYS workbench simulation. And finally, we will see a comparison of the results with the experimental measurements. Well, as we know, also in off-highway power transmission system field, electrification is becoming more and more a relevant topic because of the strengthening of emission regulations and the need for less fuel consumption. And this leads to the typical use of high rotational speeds of the e-motors that leads to an increase of power losses and temperatures. And these two aspects has to be controlled as the temperatures leads to possible overheating of the internal components, and the power losses must be controlled in order to maximize the efficiency of the transmissions. The case study under investigation is a transfer box for an electric compact wheel loader. The total ratio of the transfer box is about 4.86, and the transfer box is characterized by an input-output axis, overall axis of 220 millimeters. And the transfer box is composed by an input shaft, an idler shaft, and an output shaft, each of which is supported by two ball bearings. The aim of the analysis are to investigate the influences of the two different input speeds of the input shaft, as well as two different input rotational speed, clockwise and counterclockwise of the input shaft. In terms of HTC, in terms of overall HTC heat transfer coefficient, as well as churning losses, and then temperatures. Overall, in this workflow, the aim of this workflow is to validate this type of analysis for gearboxes analysis thermically point of view. And so the temperatures are being compared with the experimental results. Regarding the model setup, we used 0.8 particle size, and this leads to a number of total particle size higher than 2,300,000, and the simulation for the HTC and conjugate heat transfer analysis has been performed on a workstation with a GPU NVIDIA RTX A500. The results of the heat transfer coefficient analysis shows that, first of all, bearing lubrication is guaranteed in all conditions, and we can see that considering the same input speed with 1000 RPM at the input shaft, we can see that the different rotation of the input speeds, counterclockwise and clockwise, leads to a different distribution of oil inside the transmission, both for lower idle and for the higher idle. This oil distribution leads to a HTC map on the housing, internal surfaces of the housing, that is different for the case of counterclockwise rotation and clockwise rotation. This is for the frontal view of the transmission, and this for the rear view. The results are similar as the front view. Now the question is how those HTC map influence the temperature on the gearbox, considering that we have different power sources generation due to bearings, seals, and churning losses of the gears. We estimate the power sources, these power losses, that is the power sources of the thermal analysis, according to the formulation provided by technical report of the ISO 14179 Part 2. Power losses are, in few words, the differences between the input and the output powers, and are defined by different contributions. The first contribution is the friction of gears and the friction in bearings, and these two contributions clearly are load dependent. Then there is a contribution of sealings, contribution of the churning losses of both gears and bearings due to the oil splashing, and those are the contributes for the load independent conditions, and those contributes have been compared with the experimental test. And then there are other contributions. We have to keep in mind that our aim is to minimize the power losses, and so increase as much as possible the overall efficiency of the transmission, and with this goal, Particleworks can help to reach this goal, analyzing the churning losses on bearings and gears. So for our application, we have 3 different shaft seal power losses at the input shaft, and 2 at the output shaft. We have the contribute of the bearing churning losses for the 6 bearings, And then we have the churning losses contribute for the gears. It is worth noting that the technical report formulation does not take into account the different contributions, the sense of rotation of the gears, the presence of carter or cover for protect the gear from oil splashing. Does not take into account also the contribute of the gears over the oil level as the idle and input gear. And for this contribute does not take into account the oil temperature. And so we use the previous HTC simulations to estimate the churning losses, overall churning losses of each case study. And we see that, as we know, first of all, the presence of carter and screen has a great influence on the churning losses, because the output gear is true that is the higher contribution to the overall churning losses, but is quite protected by the oil splashing. Then we can see that also idle and input gear has its contribution to the overall churning losses. And for this fact, we use the different percentage of these churning losses to split this estimation given by technical report to the different gears. We used also, we apply this power source not to the entire shaft, but only on the outer portion of the gears, as is the portion of the gear that is in contact with oil. The thermal analysis heat fluxes that we take in consideration during the thermal simulation are the heat conduction between internal components, the free convection between the housing and the seals with the ambient, and so the internal forced convection due to the oil distribution, that is the HTC map. Before going ahead, we compare the experimental power losses with the ISO theoretical power losses for the no-load case, and we saw that there is the different contributions leads to a certain gap between the experimental value. We try to substitute the churning losses calculated by ISO and with the churning losses provided by Particleworks, and we see that this gap can be reduced for all cases. For the thermal analysis, we proceed step by step. And first of all, we start with a project in collaboration with the Mechanical Engineering Department of Padua University, analyzing two different simulations using ANSYS workbench as a thermal FE solver. In the first simulation, we consider only the power losses given by ISO, and for this case study. And in the second simulation, we consider, in addition to these power losses, the HTC map given by Particleworks. And we see that the percentage error given by the two simulations is quite different. And in the case with HTC map, we have a maximum error of 15% with respect to the other that was 50%. And so we can say that HTC map cannot be neglected in this kind of thermal analysis in order to better approximate the experimental values. We see that with the thermal analysis, CHT analysis in Particleworks, we see that the temperature distribution inside the transmission is in accordance with the powers, input power losses in bearings, external portion of the gear, and input seal, for example. But the most important result is that we see that different HTC map for the counterclockwise and clockwise input rotations at same speed leads to two different temperature distributions. And in particular, we see that the clockwise case study has a higher temperature than the counterclockwise simulation, in accordance with what we found in experimental tests. The following step is to compare Particleworks CHT solver with the ANSYS Workbench 1 for this specific case study, and compare the thermal outcomes with the experimental values acquired with the thermocouples inside the gearbox during the validation test. And as we can see in this tab, the different temperatures of the 6 bearings under investigations, we can see that each these values are the gap between the simulated temperature and experimental one for the different bearings and in the two simulations. And we can see that the two simulations are in accordance, and we found a minimum gap about 4 Celsius degrees and a maximum gap of 15 and 17 Celsius degrees. Worth to be noted that this value, the higher gap, is in correspondence of the input bearings near to the input seal that has a very high power loss input according to ISO formulations. Then all thermal steady state simulation has been performed on all the case study, and as we said before, we saw that also at higher RPM, we see that this area is higher in clockwise case study than the same area in the counterclockwise case study, in accordance also in this case with the experimental data. These values are the gaps for each case study and for all bearings with respect to experimental results. And you can see that there is a maximum value of 17, 18 Celsius degrees, and the mean gap is about 9 Celsius degrees. For all this simulation, as we said before, only the HTC map of the housing has been used, and the second iteration has been performed in Particleworks conjugate heat transfer analysis, considering also the bearings and seals HTC map. And with this HTC maps added to the previous one, we see that all the gaps are reduced, and the maximum and the minimum gap has been reduced. A final slide. As a final slide, we took the previous temperature measurements and we plotted them on this graph in order to evaluate the correlation between experimental and simulated values. Each point is a bearing, let me say, for each case study, defined by in the x-axis by the measured experimental temperature, and in the y-axis by the simulated temperature. If those are equal. All the points has to be in line with the solid line that represent ideal correlation, but in our case we have this dotted line. In conclusion, we can say that workflow for the thermal analysis of this kind of gearboxes has been tested and validated, and theoretical pulp power losses in accordance with the technical report ISO 14179/2 load independent case has been calculated and compared with experimental results, and then used as input for thermal analysis, steady state analysis, both in thermal FES solver of ANSYS Workbench and CHT solver of Particleworks. We saw that HTC maps cannot be neglected in this kind of simulations in order to better represent the experimental measurements. And we saw how with the second iteration, the HTC map of bearings and seals, in addition to the HTC map of the wall housing, has decreased the maximum and the mean gap of the bearing temperature with respect to the experimental data. Next steps could be for sure the implementation of the air inside the transmission and in the HTC model, and decrease the simulation time with multi-particle size approach. Thank you.
Thank you, Massimo. Very complete presentation. Any questions from the audience?
Hi everyone, thank you for your presentation. Can I ask you about computational time of this simulation and particle size?
Yes, we simulated 5 seconds of simulation for each case study, and as you can see here, those are the values for each case study with this number of particles.
Thank you. I missed it.
It's about 1.34 for each second of simulation.
What is the time to let the flow stabilize? How many seconds?
Is 1-2 seconds. 3-4 seconds, as we can see here. This is not the time, okay, but is the total simulation is 5 seconds, and we can say that after 2 or 3 seconds, the flow is stabilized.
Okay. Other questions? Thank you. Hello, I was just wanted to ask, you spent some time on evaluating the losses analytically, or from a standard way of evaluation, and also the churning losses from Particleworks.
Yes.
And so then later you had to input this into the CHT simulation. So you just evaluated this as volumetric heat sources in the solids, or how did you incorporate the heat sources of the losses?
We incorporate this kind of losses here. For each gear, we use the total gear tuning losses value given by ISO and split this value in a percentage given by the percentage outcomes of Particleworks HTC and oil flow analysis. And as you can see, for example, the total value given by ISO for the output gear has been multiplied by 0.51. That is the percentage of the outer gear, of the output gear, with respect to the total churning losses of the simulation.
Okay, thanks. So then it's in the CHD, it's input as a volumetric source to the whole wheel.
And right? Yeah, not to the whole gear, but only to the outer portion, as you can see here.
Yes. So you have modified the model to have
sure.
some surface layer.
Yeah, sure.
Okay, perfect. Thank you.
For each gear.
Thanks.
Thank you.
Hello, thank you very much for the nice presentation. I have a couple of questions. I think in one of the slides, I believe number 17 or something like that, you showed that there was a significant error on one of the measurement positions. I think it was T3.
Yes.
Did you make any specific reflection on why that position was so much off?
As I said before, probably is due to the very high power input losses of this input seal, and ISO formulation for this kind of power losses probably does not reflect the experimental behavior of this kind of seal.
And then still related to that, did you use ISO? Did I understand well? You used ISO formulation for seals and bearing losses. You haven't used any more advanced approach?
No, we start with this baseline approach, but sure, for following analysis, there are a lot of literature formulations that can be used.
Thank you.
Thank you.
Hello, hi. I want to ask you about the heat transfer coefficient with air outside. So I don't know if you can tell the value you use and how you guarantee that on the test bench, because a small test bench is full of fans and everything, and sometimes a small air movement can change that. So I don't know how you do it.
We estimate that from experimental data, and we does not use a fan in this test, and we estimate it from experimental test. In after 2 hours of test, and so is in steady state conditions.
Okay, so it was not forced convection.
No, the external no.
Hello. In terms of percentage difference of the thermal gaps, you have shown
Yes.
only values in delta T
Yes.
of temperature. These values in percentage against the measured values, experimental measured values?
Yes, are not very far from the experimental values. Overall, I can say from 5 to 10%, also less.
Okay, thank you.
Thank you.